All right, good morning, everyone. So we're going to go ahead and wait a couple more minutes so that we can get a few more viewers, and then we'll start talking about quantization of energy and the properties of light today. All right, we'll give it 1 or 2 more minutes, and then we'll go ahead and get started. And just as a reminder, if you haven't done so already, please accept your invitation to go to your breakout rooms so that we can all work in groups together on problems today. Okay, great. So we're going to go ahead and get started. So today we're going to be talking about quantization of energy and some of the unique properties of light. So first off, I wanted to review some of the important concepts that we discussed yesterday. So yesterday we found that the velocity of a wave is equal to the wavelength times the frequency. So just as a note, yesterday I used mu to describe frequency, but today I'm just going to use the letter F. That's because later in the presentation today, we're also going to be talking a lot about velocity, which is a v, and the v and the mu look very, very similar. So to keep things clear, we're going to represent velocity with a v and frequency with an f. Okay. And then the other important concept from yesterday was that waves are additive. So a fancy word for this is the principle of superposition, but what this basically means is that if you have interacting waves or interfering waves, that you can just add up the amplitude or displacement at every single point, and then you can get your new wave. And so we also talked a little bit about electromagnetic waves. So electromagnetic radiation consists of oscillating and perpendicular electric fields and magnetic fields. And the special thing about electromagnetic waves is that they all travel at the same speed. So by definition, they all travel at the speed of light, and that has been determined to be 3 times 10 to the 8th meters per second. So then you'll often commonly see this written as lambda times F equals c, because c is just a common letter we're going to use to denote the speed of light. So hopefully all of those concepts are clear and that the problem set last night really helped if anyone had any questions, but still feel free to post any questions about this in the chat or stay for the office hours in the Zoom room afterwards. Okay. So today we wanted to introduce the concept of quantization of energy. So back in the 1900s, disagreements between experiments and some of the classical physics theory led physicists to develop new theories. So previously, classical mechanics had the idea that all energy was continuous. So any real value of energy is allowed. So if we plotted the function of energy, you would get a line or some continuous function, right? So every single value is allowed because this is a continuous function. So someone asked in the chat, are all electromagnetic waves transverse? Yeah, they all are transverse waves. I believe so. Okay. And then quantum mechanics, which is the sort of modern take on physics, states that not all energy values are actually allowed. Energy is discrete, which is another way of just saying that you can only have certain values of energy. So if we were going to draw the same concept on a graph of energy, we would draw distinct lines that can only happen at certain values of energy. So this idea was really, really important, and it changed the way that we think about how we use energy in physics and chemistry. So Max Planck proposed that only discrete values of energy can exist, and this concept is broadly referred to as the quantization of energy. And then Albert Einstein went and applied this theory to light. So one example of quantization is the US money, right? So if you think about what's the smallest unit of money you can have, that would be a penny. So you could think of, you can only have integral numbers of pennies in like prices in the US economy. So quantization is all around us. So hopefully that helps kind of clear up the idea of quantization of energy. It really is just that only certain values of energy are allowed. And that's the same way as just thinking of money can only be in terms of integral numbers of pennies, whether that's thousands of pennies or just 1 or 2 pennies. Okay. And so this idea, it was actually the beginning of modern physics, or as some people call it, the quantum revolution. So when people talk about the beginning of something called quantum mechanics, it's often rooted back in this discovery. So hopefully that makes quantum mechanics sound less scary. Really all it is just a different way of thinking about some of the concepts that you guys have already learned about in classical physics. Okay. So let's discuss more some of Planck's theories. So he said that the exchange of energy between matter and radiation must occur in something called a quanta. So a quanta is just a little packet of energy. So think of it just as like a coin, except it's made of energy, but it can still only come in discrete quantities. So this means that only certain values of energy are possible. So this is just another way of saying that energy is quantized. And he proposed the following relationship between energy and the frequency of the radiation that has been quantized. So this relationship is E equals HF, where H is called Planck's constant. So this constant is another good one to kind of have in the back of your head. It will come up pretty often in your chemistry classes. So it is 6.626 times 10 to the minus 34th joules seconds. So the units are a bit unusual, but they do work out. Just remember to always use dimensional analysis to check. Okay. So let's think about what this quantization of energy actually means. So say you have a bunch of ice cubes. If you wanted to plot the energy of those ice cubes, you could say that the ice cubes have some initial energy right now. And then say you put your ice cubes out in the sun. The sun emits light. So that means that there'll be some electromagnetic radiation coming from the sun. And this radiation will have a characteristic frequency. And we can use Planck's relationship to calculate the energy of that light. So then we can ask ourselves, what happens to the energy of the ice when it's now been exposed to the sun? So the energy would go up to some final state, but that the difference between the initial and the final state has to occur in integral values given by Planck's constant times the frequency of the light. So hopefully that example kind of helps clarify what we mean when we think about quantization of energy. We're really saying that you can't have sorted any value of energy. There's only a few possible states that can ever exist. So Einstein then extended Planck's theories to all electromagnetic radiation, such as light. So he proposed that all light is made up of discrete energy packets called photons. So this is pretty similar to the word that Planck had previously used called quanta. So photons are all just energy packets of light. So if the coin example is helpful to think of that, where photons are just small little packets of light. And the energy of a photon obeys Planck's relationship. So that means that the energy is proportional to the frequency of the light, or the frequency of the photon. And again, here we also use Planck's constant, which is defined exactly the same way. So we can use this equation to actually calculate the energy of light. So now in your Zoom breakout rooms, I'd like you guys to do a quick example. I put down some of the equations and constants that could be helpful here, but please go through and calculate what the frequency of a beam of light would be if each photon in the beam has an energy of 4.44 times 10 to the negative 22nd joules. And feel free to also post any questions about anything we've discussed in the chat as well. Does anyone need more time? If so, just let us know in the chat and we can give you guys more time. And also as a reminder, if you're watching this live stream, please also join the Zoom rooms. Okay, great. So no one said they need more time, so we're going to go ahead and go over this example. But again, please still feel free to ask questions. So we can rearrange this equation for energy to solve for the frequency. So in this case, frequency would equal the energy of the photon divided by Planck's constant. So that you can write out these numbers here, and then you would get 6.7 times 10 to the 11th, 1 over second. And again, like we learned yesterday, 1 over second is another way of writing hertz, but hertz is the most common unit that we use to write frequency. So then we would rewrite this as 6.7 times 10 to the 11th hertz. And that would be the frequency of this beam of light. Okay, so now I'll give you guys a quick 1 to 2 minute break just to kind of think about those concepts and ask any more questions, because then we're going to move on to an example that is a bit more complicated and really relies on everyone having a good understanding of what we just did. Okay, great. So it doesn't look like there's any questions, so we're going to go ahead and move on. Okay. So there were several experiments that exposed some of the issues with classical physics and led us to develop new sign. Okay. What was the difference between a quanta and a photon? So they're very similar ways of thinking about the same thing. So quanta apply to all energy. So all energy is broken down into these discrete packets called quanta. Photons applies just to light. So that would be only that specific kind of energy. Great question though, but the concept is the same in that they're still quantized forms of energy. Okay, great. So several experiments kind of exposed some of the issues with classical physics and led us to kind of decide on new theories. So there were kind of 3 main experiments that did this. So the first one was black body radiation, and then there were some diffraction experiments, and the last is called the photoelectric effect. So all of these are really important, and you're going to talk about all of them in Chem 1A, but we just wanted to talk about one today and kind of go through the math and the physics behind that experiment in more detail. So we're just going to talk about the photoelectric today, but if you are curious about some of these other experiments, please come talk to us. If not, I can guarantee you will see it at the beginning of Chem 1A. Okay, so first off, let's describe what the photoelectric effect even means. So say we have a block of metal. We can also depict this metal using all of the atoms inside of it. So we know there's going to be the positively charged nucleus, and then there's all these electrons around in the metal. So hopefully that all makes sense from some of what we discussed in week 1. And now, say you shine a beam of light at the metal. So again, a beam of light and a photon are now the same thing. So again, just make sure that that definition is in your head. So suppose we hit this piece of metal with a beam of light. What would actually happen? So what ends up happening is that we will eject an electron from the metal because our beam of light has so much energy that it will hit these electrons and it will just kick them out of the metal. So these ejected electrons are then called photoelectrons. So this is just kind of the name that people give them because these electrons were ejected by photons. So just remember that the ejected electron is then called a photoelectron. But just to summarize this experiment again, basically what we're doing is we're hitting a piece of metal with a stream of photons. And when these high energy photons hit the electrons in the metal, they will actually kick an electron out and they will cause it to fly out of the metal. And that is basically what has been called the photoelectric effect. Okay. So we can also kind of break down the photoelectric effect into energy. So because energy is conserved, we know that the final energy of the system must be equal to the initial energy. So we know that the initial energy is just the energy of our stream of photons. So we can write the following equation. Your initial energy equals the energy of your photon stream, and that, as we discussed before, is just equal to Planck's constant times the frequency of your photons. And then we can also think about what the final energy would be. So like I described previously, after this beam of photons comes and hits the metal, we have two things happen. We have the electron being removed from the metal, and then we also have the photoelectron flying away. So this photoelectron that has been ejected does have some characteristic velocity and mass. So because this particle is now moving and it has a velocity and mass, we can write a kinetic energy term for this photoelectron. However, it did also take some energy for us to remove the photoelectron from the metal in the first place. So there's also an energy associated with that. So that means our final energy is the sum of the kinetic energy of the ejected photoelectron plus how much energy it took us to remove that electron from the metal in the first place. So just to summarize, our final energy is composed of two quantities. The first is the kinetic energy of the photoelectron, and the second is the energy required to remove an electron from the metal. So we can rewrite this using the equation for kinetic energy. So kinetic energy can be rewritten as 1/2 mv squared, where m is the mass of the photoelectron and v is the velocity of the photoelectron. And just a quick definition, this term that I've denoted as energy of removal is called the work function. So this is the minimum energy required to eject an electron. And this is characteristic of different kinds of metal. So every single metal will have a different work function. But the work function is just a fancy way of saying the amount of energy that's required to actually remove an electron from this material. So that means that if you don't have enough energy to remove the electron, you won't ever be able to eject an electron. So we'll go through some examples to hopefully kind of clear up some of these concepts, but the important takeaway is that from the photoelectric effect, we can write different quantities of energy and use that to learn about the system. Okay, so let's work through an example together in class. So if you have like pencil and paper, please get that out so that we can all go through some of this math together. Okay, so let's consider an example of the photoelectric effect. Let's say that the light that is coming to hit the piece of metal has a wavelength of 525 nanometers, and this white light with the wavelength of 525 nanometers hits a piece of cesium metal, and we can ask ourselves, will an electron be ejected? And if so, what is the velocity of the ejected electron? So here I've also given you the work function for cesium. So that means that the energy removal term that I talked about in the last slide is defined to be 3.43 times 10 to the negative 19th joules. So when we get started on a problem, it's always helpful to kind of draw out a diagram and then write down the quantities that we know and identify what the quantities that we are trying to find are. So we know that our photons have a wavelength of 525 nanometers. We know that the energy it takes for us to remove an electron is 3.43 times 10 to the 19th joules. And what we're looking for is the velocity of the So let's go ahead and break down this problem into steps. So one, let's calculate the initial energy of the light entering the system. So to do this, we can use the equation that Planck proposed. So this just says that the energy of the photon is equal to Planck's constant times the frequency. So I'll give everyone around a minute to try to do this on pencil and paper as we go along, and then I'll go through and show the solution. Okay. Someone asked, does the photoelectric effect just apply to metals or any element that has conductivity? So metals are the only elements that are conductive. Sometimes semi-metals are, but by and large, the metals and elements that are conductive are the same thing. So I've only ever seen the photoelectric effect applied to metals. But I think that broadly it could be applied to any material as long as you're able to actually eject the electrons in a measurable way, and that tends to be easier for metals. So hopefully that helps answer your question. Okay, so I'll go through and also solve this problem. So if you didn't have enough time, that's okay. There'll be a separate example for everyone to work through in a little bit, but right now we'll just try to get through this in class. Okay, so we were given the wavelength of light. So first we need to figure out what the frequency of our light is so that we can use Planck's relationship. So we know that the frequency of light is equal to the speed of light divided by the wavelength. So we can substitute that equation in to Planck's equation, which gives us the following relationship. The energy of the photon is equal to Planck's constant times the speed of light divided by the wavelength. And I've written out the numbers here. So make sure that you check that all of your units are canceling out correctly. So I gave the wavelength in nanometers. So that means that you would have to convert that to meters so that all of your units balance out. And just remember from what we talked about that a nanometer is 10 to the minus 9th meters. So that was the conversion that I did down at the bottom for wavelengths to get everything into meters. So once you calculate this, you get that the energy of the photon is equal to 3.78 times 10 to the 19th joules. And then we can ask ourselves, will an electron get ejected from the metal? So another way of phrasing this question is asking, is the energy of our incoming photon beam greater than the energy required to eject an electron? And again, the energy that's required to eject an electron is by convention called the work function. So we know from our calculation we did on the last slide that the energy of our photon is 3.78 times 10 to the 19th joules. And by definition, the energy we need to remove an electron is 3.43 times 10 to the minus 19th joules. So in this case, the energy of our photons is greater than the energy required to eject an electron. So that means that an electron will be ejected from the metal. And now that we know the electron actually can be ejected from the metal, we can go forward and think about what the velocity of that ejected electron would be. I'll give everyone around a minute to kind of think about this and ask any questions in the chat. Okay, so someone asked, where did I get c in the previous slide? So let me go back. So c is the speed of light, and that's defined to be 3 times 10 to the 8th. So that's something that you would either be provided or expected to have memorized, but you would never be expected to get that out of nowhere. Okay. Does the electron return after you stop beaming light on the metal? No. Usually once it's gone, it's like flown out and it's been ejected. So it usually doesn't go back. Is this why every time we get shocked as we went down the slide as kids? No, I think that is, that's capacitance, right? Yeah, so this is not why you get shocked when you go down the slide as kids. That's because physics, other physics things. Yeah, that has to do with charges. So when materials are rubbing together, you can build up a layer of charges between the two different materials, and that the difference in charge between you and the slide causes a spark. So that's something that has to do with charges and materials. Okay. Great questions, though. Oh, let's see. Can we trap the photoelectron? How does the photoelectron differ from the electron? So you can trap the photoelectron. There are some spectroscopy techniques that specifically look and measure the energy of these photoelectrons. So they'd have like a detector, and you would place a detector so that your ejected photoelectron would have to hit it, and then you would do things like measure the energy of that photoelectron. So how does the photoelectron differ from the electron? The properties are the same. We just call it a photoelectron to kind of distinguish that it has been ejected, but it has the same mass, it has the same charge as an electron. So really it's no different in terms of properties. People really, I think, just call it a photoelectron to emphasize that it came from this event. Yeah, so I guess it's also good to clarify that it's hard to trap electrons, but you can detect and measure them. So you can figure out where they were-ish, but not really, you can't really ever trap them. Okay, so let's move on to the next part of the problem. So we can ask, what is the velocity or the kinetic energy of the ejected electron? So you can calculate this by relating the initial energy of your system to the final energy of your system. So because energy is conserved, we know that these must be equal. So that means that the energy of your incoming photon has to equal the kinetic energy of the ejected photoelectron plus the energy required to remove that electron from the metal in the first place. So that's summarized in this equation I have here. And once you write out this equation, you can basically solve for the velocity term, and that would give you the velocity of the ejected electron. So we had calculated all of these things previously, so we know that the energy of our incoming photon stream is 3.78 times 10 to the minus 19th joules, and that the work function gives us the energy required to remove the photoelectron, and that's equal to 3.43 times 10 to the minus 19th joules. So you can do some algebra and rearranging, which I haven't shown here, but that would give you a velocity of 2.8 times 10 to the 5th meters per second. So that's how you would actually answer this question, is you would say, yes, the electron has been ejected and it's traveling now at a velocity of 2.8 times 10 to the 5th meters per second. Okay, so now in your groups, let's do another practice problem. So if light with a wavelength of 625 nanometers hit a piece of cesium metal, would electrons be ejected? And if so, what is their velocity? So again, I've also given you the work function for cesium, which is 3.43 times 10 to the minus 19th joules. So go ahead and work on this in your groups. All of these slides are also available on B courses. So if you want to go back and refer to some of the past equations, you could go and download it from B courses too. So someone asked, would we use the mass of an electron? Yes, you would. So it's a really, really small quantity, but it does contribute some amount of energy. So I'll give you all around 5 minutes for this, and then we'll come together and discuss it. And feel free to continue asking questions about the example we just went through as well. I know this is a lot of information at once. Okay, so I'll give everyone around 2 more minutes. If you think you'll need more time than that, feel free to post in the chat and we can always wait longer. Okay, what is the mass of an electron again? So we'll go ahead and post that in the chat. Okay, does anyone need more time? Otherwise, we'll go ahead and get started in a minute. Okay, great. So we'll go ahead and go over this example. So similar to before, our first step would be determining the energy of the incoming photons. So we would do this by using Planck's equation. And again, this time we have also been given the wavelength of light and not the frequency. So first, we would want to write frequency in terms of the speed of light and wavelength. And then we substitute that equation into our equation for energy of photons. So that would give us the following equation. Energy of photons equals Planck's constant times the speed of light divided by your wavelength. So you can write all of that out, and then you can solve for the energy of your incoming photon. And you would get 3.2 times 10 to the minus 19th joules. Okay, and now we can ask, will an electron get ejected from the metal? So again, this is just another way of saying, is the energy of the photon beam greater than the energy required to eject an electron? So we had calculated before that the energy of our incoming photon beam is 3.2 times 10 to the minus 19th joules. And we know that the energy required to remove an electron is given by the work function. So this is 3.43 times 10 to the minus 19th joules. So you can see that the energy of your incoming photons is actually less than the energy required to eject an electron. So because your incoming photon stream doesn't actually have enough energy to even remove an electron in the first place, you will not be able to eject an electron from this material, which then means that the second part of the question is irrelevant because it has never been ejected. So then there is no velocity because you don't have a photoelectron. Someone asked, how does the power always equal minus 19? Because I picked numbers that added up to always be like that, I guess would be the y, that is y. But really all we've done is change the wavelength from like 520 to 625 nanometers, which is really a small change compared to the order of magnitude of the other numbers in those equations. So that's why you're always going to have the same order of magnitude of 10 to the minus 19th. So all of these numbers are ones that are kind of expected from what work functions for metals would be. So yeah, around 10 to the minus 19th joules is kind of a common threshold for this. Yeah. Okay, great. So sorry for those of you that went through and calculated all of the velocities, but the trick of this is that the energy of the photon is actually less than the energy required to remove the electron, so you would not get an ejected photoelectron. So someone asked, how do we get the value for C again? So the C is the speed of light, so that is something that you should either have memorized or would be given to you. So that is defined to be 3 times 10 to the 8th meters per second. So just going back to that slide, that is. And the speed of light is always the same. So no matter what wavelength of light you have, it will always be traveling at the exact same speed. and that speed will always be 3 times 10 to the 8th meters per second. So that's something that, again, is special about electromagnetic radiation, which is a class of light, is that it will always be moving at this exact same speed, which is why we've written it as c instead of just as velocity. Okay. Great. So the main takeaway of the photoelectric effect is that this effect can actually only be explained if light is a particle. So that may be kind of weird, right? So the photoelectric effect supports the idea that light must behave like a particle, and that all electromagnetic radiation behaves like a particle. Okay, so someone also asked, will the mass of an electron ever change? No, the mass of an electron, I can't think of an example where it changes. I don't think it ever does.
It's not an electron anymore.
Yeah, that's the characteristic mass of an electron. Okay, so we also know from other experimental evidence that light must act like a wave. So in order for both of these things to be true, that means that light must act like both waves and like particles. So this concept is referred to as wave-particle duality. But that's really just a fancy way of saying that light will always behave like a particle and a wave. And this is actually true of all electromagnetic radiation. So this concept was actually extended further. So in 1925, a guy called Louis de Broglie proposed that all matter must have wave-like properties. So he then related the wavelength of the matter wave with the mass and velocity of the matter particles in something called the de Broglie relationship. So again, the distinction between what we're talking about now and what we just talked about on the last slide is that now we're applying this concept to matter. So before we were saying that light and electromagnetic radiation can behave like a particle or a wave. Now what we're saying is that even matter, which is something we think of as behaving like a particle, will also behave like a wave. So that means that matter also behaves, it follows wave-particle duality. So we can write out the de Broglie relationship, and that is the following equation where the wavelength of your wave is equal to Planck's constant divided by the particle's mass and the velocity of the particle. So this is one of those fundamental relationships that is hard to derive. So we can also rewrite this in terms of other quantities that you may have seen in physics. So for example, mass times velocity is another way of writing linear momentum, which we represent using the letter P. So the linear momentum of a particle is always the particle's mass times the particle velocity. So we can substitute that into the de Broglie relationship, and we would get the same equation written in a different way. So this is the wavelength of your wave is equal to Planck's constant divided by the linear momentum of the particle. Okay. So does anyone have any questions on this relationship or what it means? I'll give everyone around 1 to 2 minutes to think about it, and then we'll move on to an example problem. Okay, great. So we'll move on to the example, but still feel free to ask any questions in the chat and we can go ahead and answer those. Okay, so our practice problem, calculate the wavelength of a particle of mass 1 gram that's traveling at a velocity of 1 meters per second. So I've given you the equation and Planck's constant that may be helpful for this calculation. And then also based on this calculation, think about why it took people so long to notice that matter has wave-like properties. So I'll give everyone around 2 to 3 minutes to do this calculation and then talk about the last part in groups. Okay, so I'll give everyone another minute. If you think you'll need more time, please post in the chat. We can always wait longer. Getting old is rough. Okay, so we'll go ahead and go over this example problem. Okay, so using these equations, we know Planck's constant and we're given the mass and velocity of your particle. So you would substitute all of those factors into the equation and that would allow you to calculate the wavelength. So you would get a wavelength of 7 times 10 to the minus 31 meters. So then, based on this calculation, why did people not notice that matter has wave-like properties? So if we think about a wave that has a wavelength of 10 to the minus 31 meters, that's actually extremely small. So just for reference, a nucleus is on the order of 10 to the minus 15th meters. So 10 to the minus 31 meters is actually so small it's undetectable. And that's why it took everyone so long to figure this out. It's just because we had no way of detecting a wave that had a wavelength that was that small. In fact, it's still so small that it's really undetectable. So hopefully that gives some perspective on how all of the matter around us is actually behaving like a wave, even though macroscopically to us, we think of all of these objects as stationary particles. It's simply because they're oscillating at waves that are too small for us to notice and too small for us to really detect. Okay, so just to briefly summarize some of the main takeaways from class today, the first is that energy is quantized in discrete packets. Someone asked how come the mass wasn't put into SI units. How did the joule cancel out? So the joule is kilogram per meter second squared, so that has a kilogram in it. The answer to the question about how come the mass wasn't put into SI units, the question would be because I forgot to type it out in the equation here. So that's why. So if you convert that to kilograms, this example should still work out. I think I just forgot to write it on the slide, but it should be kilograms. But you would just convert a gram to a kilogram by dividing by 10 to the third, and that would give you kilograms. Does that clear things up? But yeah, it's a good point that you should always convert things to SI units, so I do apologize for not writing that out. I'm pretty sure that the final answer is still 7 times 10 to the minus 31 meters, but that when writing out the equation, I put 1 gram when it should be 0.001 kilograms instead. Okay. Yeah, I did round. Just because we were only given one significant figure in the problem, I rounded it off to one significant figure in the answer, just to be consistent. Okay. Great. So again, just to summarize, energy is quantized in all of these discrete packets. So if we're talking specifically about light, then the energy would be quantized in packets called photons. And if you think about what quantization is, it just means that only discrete quantities of energy are allowed. So this plot here kind of depicts that, where now you have just fixed energy points that are possible instead of like a continuous curve. Only certain values of energy are possible. And the other main takeaway is that light and matter are properties of both waves and particles. So this is a really important concept moving forward in chemistry and physics, because this changes a lot of the ways about how we can actually represent materials. So tomorrow we'll talk more about how this impacts spectroscopy and calculating the energy of electrons and atoms. But hopefully this provides sort of the wave physics and quantum mechanics background to help everyone understand some of the questions we'll talk about tomorrow. Okay, so that is all we had for lecture today. So we ended about 3 or 4 minutes early, but please still stay around in our Zoom hours if you have more questions, or you can always reach out to us via email or any of the tutors as well.